Hello. In this lab, I found the mass of a black hole using the relationship between the net force and the rate of change in momentum. I was given position data of a star orbiting the black hole, the mass of the star, and the black hole position. I then created a computational model to find the net force of the black hole on the star. By using the law of universal gravitation, I found the mass of the black hole to be 1.97 times 10 to the 31st power. This is almost 5,500 times more massive than the star. Here you can see the law of universal gravitation rearranged to solve for the mass of the black hole. The mass of the star is given to us, and g is a constant which equals 6.7 times 10 to the negative 11th power. We find r by finding the distance from the star to the black hole at the time where we calculate our force. This will be further explained in the computational model. By using Newton's second law, we calculate the force based on the change in momentum. Now let's look at the computational model. First, we input the mass of the star. Next, we import the position data of the star as it orbits around the black hole. Our first while loop computes the velocity of the star at each position point by dividing the change in velocity by the time step. Our second loop is used to find the force. First, we have to establish the initial and final velocity and momentum vectors. Then, we find each change in velocity and momentum by subtracting the final from the initial. Next, we find the rate of change in momentum by dividing the change in momentum by the time step. Then, by Newton's second law, we can equate this to the force and then calculate the parallel and perpendicular components of force. After running our computational model, here's what we get. Because of our print statement outside of the loop, we can see the F net at the final position and the final position of our star. The arrows represent the forces acting on our star, and the green line represents its path around the black hole. Now, let's calculate the mass of the black hole using the law of universal gravitation. We rearranged the formula to solve for the black hole earlier. G is a constant and equals 6.7 e negative 11. The mass of the star is given as 3.63 e27. Using the final force shown from our computational model, we know it is 2.86 e23. Now, to find r, we take our final x and y position points and subtract them from the black hole's position. We can then use the Pythagorean theorem to find the distance r. By plugging in values, we find that the mass of the black hole is 1.973 e31. What does it mean? F net and the rate of change of momentum are actually different. In fact, F net is the cause of the rate of change in momentum. This is why these quantities are equal. F net causes the change in momentum, and it can be broken up into components. The parallel component is responsible for the speed, and the perpendicular component is responsible for the change in direction. What if? Imagine our black hole was replaced with a different black hole. In fact, the position points would have to change since they're going to be affected by a different force from the black hole. If the black hole was more massive, it would exert a greater force and cause a tighter or closer orbit. A wider orbit would result from a less massive black hole. So in short, no, we would not be able to find the mass value for the new black hole. Once again, in conclusion, by using Newton's second law and the law of universal gravitation, we took position points and the mass of a star orbiting a black hole whose position was known to find the mass of that black hole. By creating a computational model, we found all the needed values and found the mass of the black hole to be 1.973 e31 kilograms, which is about 5,500 times more massive than our star.